Hello everyone, my name is Mengyu Wu from PUF Security RD team. Thank you all for joining this webinar. Today I am very honored to have this opportunity to introduce you our new product, PUFiot, the PUF-based secure coprocessor. PUF Security announced the PUFiot early last year. After that, we added a sequencer, cryptographic engines, security protocols, and key management unit based on PUFiot. By this way, we make a new secure coprocessor, PUFiot. This presentation will also discuss the design concept of PUFiot, design architecture, and how to use it in a secure SOC. In addition, the application of PUFiot will be briefly introduced. The PUFiot can fully implement secure operation, secure storage, further secure supply chain, and silicon lifecycle management. About supply chain part will be introduced in another webinar. I hope everyone can get some valuable information from my today's talk. This is my agenda today. First, I will quickly introduce some basic knowledge of the hardware root of trust. Second is the design concept of PUFiot, its architectures and how to integrate it into a SOC. The third part is how to use PUFiot in some applications. The last few pages are about some comparisons and advantage over other solutions. Before PUFiot introduction, I would like to recall and introduce hardware root of trust again. The security systems can be divided into three levels. Application layer, usually related to applications or services. Second is the software layer. Third is the hardware abstraction layer, includes firmware, API, and hardware design. The security of the systems comes from a design code, the root of trust, which is usually implemented using hardware. The hardware root of trust needs to consider to follow three important principles: trusted storage, security ring, and secure operation. First, for trusted storage, it's a secure OTP with tamper-proof design. Second, for security ring, it can be built by dedicated logic, RAM, non-volatile memory, and to use entropy from PUF or true random number generators to protect the static storage, dynamic storage, and crypto operations. Third, for secure operation, the operation shall follow secure policy and use crypto engines and protocols to protect the root of trust. Here, let me introduce and recall the Neopath technology of in-memory again. In-memory announced Neopath technology at 2018 ISSCC. By using the design of two MOS capacitors and the quantum tunneling competition, the device coin with entropy was invented. Through statistical analysis from mean entropy using NIST-SP890B and NIST-SP822, Neopath can be defined as a perfect steady entropy with ideal randomness, uniqueness, and stability. Neopath is a real hardware PUF, no need any helper, immediately ready in microseconds, and can achieve 0-bit error rate in all process, voltage, and temperature corners. Regarding traceability, because the precise energy control is used in the entropy generation process, there will not be any physical marks generated. So there is no physical or electrical analysis that can reverse Neopath entropy. In addition, according to the gamma ray radiation experiment, Neopath also shows the characteristic of radiation hardened, which is suitable from car industry, military to aerospace applications. Moreover, Neopath can mass production from 5 nanometers to 0.15 micrometers without worrying about reliability and yield loss. First of all, I would like to explain our main concept for building the hardware root of trust. From the diagram on the left, we create a chaotic ring by using static entropy from PUF, dynamic entropy from two random number generators, and tamper-proof shell to protect the central OTP with sensitive data. Unknown static and random numbers can well protect static stored data. The dynamic random number can protect the macro operation and can be used for the further security operation for secure SOC. Combined with anti-fuse OTP, this hardware root of trust will be a trusty block that can resist hackers' attacks. We call this product PUFiot. This is the first IP of PUF Security. PUFiot directly provides a tamper-proof shell, two random number generators, secure storage OTP, and PUF. It's very easy to adopt in security systems that require the three basic primitives. In the diagram on the right, we have further added NIST-compliant cryptographic engines based on PUFiot to provide security boundary for key storage and key management. It's a secure coprocessor to support trusted storage, secure PUF-based boundary, and secure operation. Currently, PUF Security has designed these two IPs to support each security systems based on this protection concept. Today's talk, I will focus on PUFiot. This slide quickly shows PUFiot's features and how to integrate it into a system. It has several highlights. First, it has the old features of PUFiot with integrated, secure, trusted storage, two random number generators with embedded jitter noises, and PUF for inborn HUK and attestation key. These inborn keys can greatly save the costs for key provisioning and building secure clean room. Second, it has cryptographic engines around the PUFiot. It can support key generations, block ciphers, digest hashing, symmetrical and asymmetrical authentications, and key exchange protocol. Please note that PUFiot's cryptographic hardware accelerators already passed NIST CFVP certification. Third, the PUFiot has designed XI and HB master DMA, directly memory access, for unloading CPU for moving data and embedded MMU, memory management unit, for classifying different keys, policy, and secure range. Fourth, all algorithms and protocols are designed using embedded sequencer with specific microcode. No CPU is required. It's easy to use for any systems, and no OS or boot code is required. It's a drop-in replacement design and easily enhances the SOC security. PUFiot is suitable for open secure systems, closed systems, or lightweight IoT. Finally, because PUFiot itself has an unknown HUK to protect each system, the local key from PUF can be used to encrypt the entire system, which is equivalent to directly extend the secure boundary to any subsystem. General storage, such as flash memory, can therefore be further converted to secure storage. This table shows the PUFiot spec for your reference. It features one on-chip HUK of 256-bit, high-speed and low-power true random number generators, AKB secure OTP, a standard APP client interface, DMA channel in SI host or HB host, and a memory management unit for controlling key temporary storage and policy. The cryptography in PUFiot has public key, accelerators, block ciphers of AES and SHA-2. Therefore, PUFiot can support private and public key generation, key exchange of ECDH, and authentication of ECDSA, followed by NIST curves. Of course, symmetrical authentication of CMAC or HMAC are included. PUFiot also supports NIST standard key derivation function and key wrapping function. We also provide firmware and API for use by the driver layer and application layers. They can achieve secure boot, key management, and more modern video device onboarding. Most importantly, PUFiot with cryptographic engines pass the NIST CFVP certification on algorithms and protocols. The tamper-proof design in PUFiot passed the third-party vulnerability assessment. This page wants to emphasize the main difference between PUFiot and conventional SOC with discrete crypto elements. First, PUFiot has dedicated secure logic, storage, and operation. The architecture follows the guideline of PSA, Platform Security Architecture, that has its own secure boundary for sensitive data management. The keys and sensitive information are well protected and only accessible in the PUFiot. No any software or public working memory can touch the key. The secure boundary of PUFiot is quite robust and pure hardware with less vulnerabilities. All secure operations such as key management, block ciphers, authentications, and integrity check can be done by PUFiot. Second, it's an integrated IP with all-in-one digital functions such as cryptographic engines and secure policy, and analog IPs of PUF, OTP, anti-tampers, and entropy source from jitter noises. We want to build an easy-to-adopt IP to create a trusted zone to easily enhance and meet the security requirements of any systems. The use of PUFiot does not require a CPU or boot code, which also means fewer CPU vulnerabilities and is easy to adopt in any system. Third, PUFHUK can help convert commodity flash to secure flash and convert NOR OTP to secure OTP. The on-chip HUK is a unique on-chip fingerprint. This means that the SOC and storage media have been paired to prevent tampering. In contrast, in a conventional SOC, since keys are distributed everywhere, including insecure eFuse storage, it will be a difficult task to cover all vulnerabilities. You have to do a lot of protection work on key distribution, working memory, and execution threads in core. Moreover, since there is no entropy in the conventional secure system, this means that sensitive data is not protected by any entropy. PUFiot can be used as a secure coprocessor to any system. There are already two mainstream CPU architectures that have already used the PUF security solutions. Whether it's an open system with trust zone in ARM, a multi-zone security environment in RISC-V, or an ARM or RISC-V cross-security system environment, it can be easily supported. PUFiot provides an integrated hardware root of trust and directly provides security functions to the main CPU. PUFiot can support various security applications. The following is an example of what PUFiot can do. Because PUFiot has an on-chip fingerprint PUF, it can use block cipher of AES with an unknown secret HUK to provide secure storage by data encryption. Because PUFiot has the NIST-certified hardware cryptographic engines and protocols, by using the verified firmware and API, secure boot, key management from seed to keys, and first trusted secure channel can be easily achieved because it has innate attestation, private key, and public key pair. In addition, because PUFiot has a secure OTP inside, PUFiot can be used to fully support chip lifecycle management from key generation, secure deployment, field use, and to the end of life. As a trusted root of trust of hardware, PUFiot can perfectly achieve the task of semiconductor supply chain and life cycle management. Next part, I want to introduce and emphasize the two main features of PUFiot. The first one is about key generation. Compared with traditional UID, HUK, or attestation key injection, PUFiot can use the enrollment operation to obtain PUF fingerprints without having to spend additional costs for having a certified secure clean room for key injection. In common practice, we would use on-chip two random number generators or HSM to generate keys, then write into OTP or non-volatile memory. It requires a certified clean room and secure OTP to protect the entire injection process, chip control, and the key access policy. By using PUFiot, there is no writing route of PUFiot to inject the cloned key since PUF is natural born, cannot be revised, and cannot be reversed, which means that the entire key generation process has less vulnerabilities, saving costs, and can easily prevent key and chip duplication. This page introduces another important applications of PUFiot, which can assist the data protections of flash memory. A SOC system usually has three kinds of flash memory, namely embedded flash, NOR flash, and NAND flash. Normally, NOR flash is used to store code and firmware, so it needs quick random access and code execution. NAND flash is usually used to store large capacity data. For example, in advanced AI chips, it's used to store the training models and algorithms software. Regardless of whether it's code or data, the assets need to be well protected. An existing threat model for counterfeiting is that hacker can read out the storage from the standard interface of external flash, or use reverse engineering to get the data in flash memory cell. PUFiot can protect embedded flash, NOR flash, and NAND flash by leveraging block ciphers and on-chip hardware unikey. Even hacker can read out the content or remove the flash chip to combine another device, since the content is encrypted and no paired key. The system cannot be further executed. Therefore, SOC and flash memory are paired and can further prevent counterfeiting. This page describes in more detail how to use PUFiot to protect flash memory. PUFiot has 3 independent accessories, which can work with PUFiot to protect flash memory. In every case, PUFiot provides local hardware unique key from key derivation function to each accessory IP. First, PUFsIP can help convert NOR flash to secure NOR flash. Code in NOR flash is locally encrypted and can be executed directly. We call it SIP, execution in place. PUFiF can help convert embedded flash memory to secure embedded flash memory. Code in embedded flash is encrypted using local key from PUF. Third, PUFenc can help convert NAND flash to secure NAND flash. Assets are encrypted in NAND flash memory. Since the data capacity is large, it needs DRAM as buffer to store the encryption and decryption plaintext data. The table on this page shows the current IP products provided by PUF Security, including PUFrt, PUFiot, and PUF Flash related solutions. First, PUFrt provides integrated macro with interface, control logic, secure OTP, true random number generators, and PUF. PUFiot, as a secure companion IP, provides PSA PUF-based enclave for providing comprehensive secure operation. PUF Flash is a solution. As I mentioned on the previous 2 pages, it's PUFiot plus the corresponding accessory IP to protect different flash memory types. According to different architectures, bus, and required algorithms, there are different options that can be configured and customized. Here is a comparison between PUFiot and other embedded SE solution. Traditional embedded SE only provides digital function of algorithm and operation. As you can see in the middle part of the table, SOC users need to find the remaining analog IPs and then integrate them into a security coprocessor. This means a lot of integration works and resources. However, PUFiot is a complete IP that integrates all IPs. Not only digital secure operations, PUFiot has all analog related modules, such as secure OTP, HUK or attestation keys from PUF, true random number generators with entropy sources, and anti-tampers have been included. Customers do not need to worry how to obtain those IPs. Just use PUFiot and go for mass production. This is the summary page. I want to emphasize again the advantage of using PUF and PUFiot security solutions. First of all, PUF Security's products can provide on-chip HUK, private and public keys without costly secured clean room. Secondly, PUFrt or PUFiot has a comprehensive anti-tampers design, which can resist invasive, semi-invasive, and non-invasive attacks. Third, our solutions already have standard interface, controller, OTP, true random number generators, secure operations, firmware, and API. It's a one-stop shopping to get what you want. Fourth, the PUF security solutions have obtained third-party certification from Resecure and NIST-CAVP, which means that IP security and correctness are guaranteed. Finally, all the eMemory and PUF security solutions can be used in almost all foundries and processes. That means using PUF security solutions will be easy to fulfill your customers' plan for technology migration and cross-boundaries porting. This is the last page of my talk today. Currently, PUF Security and eMemory are promoting the IP Go free evaluation program. It already contains all digital designs, documentations, and testing vectors for functional verification. In addition, we are going to provide a NIST-certified PUFiot versions and provide it in a non-NDA way. Users can implement PUFiot with our certified algorithms and protocols into FPGA board, or to combine their own design to emulate a real product. If you are interested, please visit PUF Security or your eMemory account manager. You can use it to complete the design before the real physical design and tap out. This is all the content of my presentation today. If you have further questions, please let me know. Thank you.